Okay, is everybody ready to start?
Yes.
Right, we've done pretty well in this conference. We've got our first no show on the second speaker. So Roger is going to give his presentation now. So he was due to speak on Thursday. It's relationship between Einsteinian and Newtonian physics. Okay, Roger, go ahead.
Okay. Right. Hello. Thank you for letting me give this talk. It's called Relationship between Einsteinian and Newtonian physics. So I'm going to get straight onto the issue of trying to connect Einsteinian physics with Newtonian physics. First from the historical perspective and then from the mathematical. So anyway, you can get rid of that top bit. Hiding the top bit a bit.
Yeah, I think you can possibly drag it down to the bottom. I've seen it on the bottom on someone else's screen. Maybe not.
I don't know.
Or you can possibly
click on the black and drag it.
Well, there's not just me that can't work these things.
Yeah. You might also be able to. Oh, there you go.
Yeah, but it's going to probably block something later.
Yeah.
Well, you can move that up.
You can zoom the slides out and then you'll have more of a margin. But anyway,
Yeah,
I can't see that.
So Einstein gave a talk on Boskowicz's theory in 1920, but he unfortunately didn't mention Boskowicz. And the talk he gave was in May 1920, and you can find it on this. It's called Ether and Relativity. No, can't move on.
No, you just press the forward arrow.
So in that talk he first talks about Newton's theory.
Roger, I'm sorry, can you speak into the microphone?
Okay.
I think it comes off.
There's a little remote one here.
Is it on?
This little fellow, if you click that to your shirt.
Okay. What do I do?
Click it to your shirt.
Saves your hand from getting.
So he first talks about Newton's theory, and then he goes on to talk about the other people who were working on Newton's theory. And these other people, he doesn't mention all of them. And the problem that they face is action at a distance or contact force. So you've got two types of forces: contact force or a force that has no contact. So the issue becomes, why are there two different types of force? I can't. Is that it? Yes. So it was a theory of trying to look upon contact forces as being distant forces that eventually led to the idea of Boskowicz's theory. So in Boskowicz's theory, there is no contact force. Everything is action at a distance. So you've got a particle and it interacts with other particles, not by coming into contact, but by what Boskowicz called a sphere of influence. And that sphere of influence later becomes the idea of the physical field. So what you're talking about really is a unified field theory, and Boskowicz is talking about it in the 18th century. So waffled on about it there. Oh, next. So we have the connections. We have Newton, and then it's Boskowicz and other followers. Then it's Einstein. And so the unified field theory is the middle one with Boscovich. So that's the historical context of connecting Newton to Einstein. When it's generally talked about with Einstein, they're saying he was looking for a unified field theory, but in actual fact, the unified field theory was 18th century between Newton and Einstein. So really, it predates Einstein, the unified field theory. It's just that he was another person working on the idea. So now we get on to the mathematics. And the mathematics connecting Newton to Einstein would be by a correspondence principle. Now I'm quoting Wikipedia, and Wikipedia calls the correspondence principle, it's a general sense, it means the reduction of a new scientific theory to an earlier scientific theory. So in the case of Einstein, you've got Einstein's theory of relativity, both special and general relativity, and you want to know how does it connect to the earlier theory, which would have been Newton. So you need a correspondence principle. So when people talk about the correspondence principle, one they normally think about is the one between quantum mechanics and classical physics, and Wikipedia also explains that. But the idea of correspondence principle really extends to special relativity, and according to Wikipedia, that correspondence principle would be special relativity satisfies the correspondence principle because it reduces to classical mechanics in the limits of velocities at speed compared to the speed of light. So when the speed of light, when you've got a velocity, an object, and it has a velocity, and that velocity is small compared to the speed of light, then it's supposed to connect to Newtonian mechanics. So I'm highlighting what's said again, the correspondence principle for Einstein and Newton, and it turns out that's a myth.
It's even Roger Penrose in his book A Road to Reality, he repeats this idea that if you take the limit of c goes to infinity, then you recover the Newtonian mechanics.
No, but it's a myth.
So, hello. If you see me pop up like this with my hat on, it's because I'm having to deal with the numerous interruptions to my talk. So I'm adding further information to deal with the interruptions post-talk. The interruption here was about what Penrose says, but what I was referring to was what is generally taught in textbooks and not what Penrose says. What Penrose says just creates more problems in relativity and not is dealt with in this talk. That is the problem with giving the lecture and being continually interrupted with diversions that are not part of what is being talked about.
It's not true. So that is generally what is taught, that the correspondence principle between Einstein and classical mechanics is for small velocities, then you get Newtonian mechanics, but that's not true. So the problem with it is time. For the Lorentz transformations, you have this equation, and the Galilean transformation, you have time as t prime equals t, and you think, and I'm just assuming these equations are familiar to everybody. And now the relevant paper dealing with this myth is by this person Rolf, who's an educator, and in the abstract for his paper he says, misconceptions about special relativity theory are common and pernicious. I address two such misconceptions: the low speed behaviour of the Lorentz transformation and the meaning of the phrase the constancy of the speed of light. I'm just going to deal with the Lorentz one. That's a myth. The Lorentz transformation does not reduce to the Galilean transformations for low speed. So as I said, the problem is with this, from the Lorentz transformation you got that. And so when it's approximately equal to 1 for low speed, you get t prime is approximately equal to that equation. And the trick being used was to think, as v tends to 0, then vx divided by c squared tends to 0. And if that tends to 0, then you've recovered the Galilean transformation for time. But that's not what happens, because as v tends to 0 can make the x of x divided by c squared arbitrarily large. So Rolf, when he talks about the low speed behaviour of the Lorentz transformation, he asked a question: does the Lorentz transformation reduce to the Galilean transformation when the ratio v divided by speed is small? And he answers no. So this is what Rolf says. He says, consider the usual pair of inertial reference frames, the prime frame moving with speed v along the x-axis of the unprimed frame, and you can read it for yourself. And it says, carries on, it says, let the ratio v divided by speed be as small as desired, but non-zero. Then it is always possible to find an event pair for which delta x, that means small interval of x, is large enough that the term with delta x dominates over the term delta t. This behaviour is entirely different from what the Galilean transformation delta t prime equal delta t asserts. So there's no connection.
I think this is saying that the reduction of the Lorentz transformations to the Galileo group disregards Heisenberg uncertainty, because that's what you're basically saying is the difference in the end.
This is classical physics.
Yeah. What you're saying is Heisenberg was only thought of in the quantum context, where you say you actually do have to consider this uncertainty between the time difference and the spatial difference, even when connecting it to Newtonian.
Well, that's going on to quantum physics. We're talking about classical physics here.
Yeah.
I mean, Einstein's relativity is supposed to be a version of classical physics, and Newton's physics is classical physics. So you're wanting one classical bit of physics connected to another classical bit of physics, and what they've been teaching is wrong.
So another interruption, this time by someone who wants to talk about quantum mechanics with its uncertainty principle. I have to point out that this talk is not about quantum mechanics and is about what Einstein wrote about relativity, so I'm dealing with relativity. It's like the defenders of Einstein's relativity have to throw in as many diversions as they can to get away with what is being talked about, so I can block things.
Right, so. So the correspondence principle, as taught to physics students between Newton and Einstein's myth. So it's a common thing taught to physics students that there's this connection between Newton and Einstein. And Ralph, who's an educator, admits what they've been teaching students is all wrong. There isn't that connection. So, to me, that highlights Einstein's relativity is not being properly understood. Einstein might not have been a lone worker. He might have had help from others, and those others might have clarified his theories better, because when you're talking about relativity, Einstein should have clarified things to us, but I'm saying he didn't clarify things properly. So, in his 1905 paper on special relativity, he acknowledges the help from his friend Bezo. So Bezo knew about it as well. But if there were others, then they were unacknowledged. And one of those possible people that were helping with the paper was his wife. So, first of all, I'm going to give this video by Sabine Hoffensfelder. She's a theoretical physicist, so hopefully this works.
Einstein's theory of general relativity has made countless correct predictions, and yet physicists are constantly trying to prove it wrong. Why? What would it be good for to prove Einstein wrong? And how could it be done? That's what we'll talk about today. First of all, I have to clarify that when I say proving Einstein wrong, I mean proving Einstein's theory of general relativity wrong. Einstein himself has actually been wrong about his own theory, and not only once.
Okay.
Okay.
I've got it.
Yeah.
Okay. So, various people have made the same sort of claim. Einstein's general relativity is correct, but Einstein was wrong about his own theory. And so, that is another suggested reason that Einstein didn't properly understand his theory. And so, if he had other people helping him with his theory, then he didn't know it completely. And so, the type of things that they point Einstein was wrong about, but his theory is correct, is the cosmological constant, gravitational waves, and the other implications of his theory, and minor mistakes, and that's it, by Bill Andrews. So it's worrying that Einstein didn't know the implications of his theories. Example I gave just then was in general relativity, but really want to just stick to problems in special relativity. It's suggestive Einstein was not the sole author of his 1905 papers, and it's a suggestion that his wife was also helping with it. So I'm going to provide excerpts from this talk by a Professor Pauline, who thinks Einstein's wife helped with his papers. And so let's go with that, see if that works.
Let's talk today about the tragic destiny of relativity. Everybody knows behind every great man there's always a great woman. So I'm going to tell you about the role of relativity, and mostly the plan is to examine how she worked with Albert Einstein for nearly 20 years.
Next bit.
This is what is known today as ETA. And they were both admitted to the physics mathematics section of And there were 5 students in the class. Minerva was the oldest at 21 years old. Albert was the youngest. And there was also Marcel Grossman, you might know the name, Louis Colros, and Jacob Erwin. So one year, Minerva left and went to Heidelberg to do 1 semester there. And because they were too close, and she wanted to have a bit of distance from Albert, but then she came back. They wanted to go together. So from the beginning, they had this shared passion for physics, music, and each other. Those two were absolutely infatuated with each other. They were absolutely in love. They spent countless hours studying together.
So they were studying physics together, and see a bit more.
The beginning of their collaboration, they started working together from the moment that they met, and they exchanged a lot of letters. Every time they were on school holidays during the summer when they were apart. So there were lots of moments, Easter holidays, Christmas holidays, and summer holidays, so they were separated, and then they exchanged lots of letters. 43 letters from Albert to Minerva were preserved and featured. And there are only 10 letters from Minerva to Albert that remain today. So these letters were published in 1987, I believe, but that's the latest edition, by Wren and Schulman in 1987. They were published. And so through this correspondence, we can really learn how they were working, how they interacted together. Radmila Miletievich is someone who, she was a history professor at Sick College in New York, and she published this Minerva, Life with Albert Einstein, and it just got published in 2013. Extremely complete study, so if you want all the details, you'll get them there. So Radmila Miletievich note that in those letters that are published in this paper, they're peppered with terms such as our new study, our research, our viewpoint, our theory, our argument, our work. So in those letters written by Albert Einstein, you see that he always says our work.
So, right. So there've been many people who tried to defend Einstein against the idea that his first wife was an uncredited co-author of his papers. But it would make sense if Einstein didn't properly understand his theories, then he had other people, maybe his wife as a joint author. And I've looked at it, and it's probably there was misogyny rife in that social atmosphere at the time, and somebody like Marie Curie, she was sort of like one of the exceptions, able to get through because it was a husband and wife team to begin with, and when her husband died, that she was able to get on. But in the case of Einstein's first wife, I'm speculating that maybe there was prejudice against her, and she failed the physics degree because the professors, being men, were prejudiced against women. But it's all that speculation, you don't really know. So, and also when it comes to having a physics paper, there would have been pressure not to put a wife's name onto it as well. So you got Einstein's paper without his wife being on it. So there's sort of like circumstantial evidence for Einstein's wife, but it's not really solid enough ground. But if there was more to it, to relativity, which needed to be explained, then it would have helped if there was a joint author to explain things better. It's all right. There's another issue of failure with the correspondence principle between Newton and Einstein on relativistic mass. So, this person is supposed to be a genius, and he wrote a lot of very influential physics textbooks for students to learn from for his the physics form. So from his textbook, he says Newton's second law, which is expressed by the equation, that equation, was stated with the tacit assumption that m is a constant, but if you decide that there's relativistic mass, then you're right in that equation. And a reference for that Feynman's lectures is there. So that would provide a simple connection between Einstein and Newton, but it fails. So Don Lincoln, he's a theoretical physicist, says there's no relativistic mass. So this is what Wikipedia says about Don Lincoln. He's an American physicist at Fermilab. So here's an excerpt from his talk.
Without a doubt, Albert Einstein's theory of special relativity makes some very mind-blowing predictions. Clocks run at different rates, objects shrink, and things can't go faster than light. And all of these things are absolutely true. Relativity has been thoroughly tested, and there is no credible criticism of the theory, although you wouldn't know it from the piles of unsolicited correspondence I get on the subject. So let's talk about that last one. The idea that you can't go faster than the speed of light. This is a well-demonstrated fact. So why is it true? If you ask a well-educated scientific layperson, they will tell you that it's because the mass of an object increases as the velocity increases. In fact, you'll hear this said by people with physics degrees. There's only one thing. It's just not true. Now, I realize that me saying that is going to confuse a lot of you, like this guy here, for example. So what's going on? Why is it that even some physicists will say that the mass of an object increases as the speed increases? Heck, why is it that even I have said that upon occasion? Don't tell anyone.
So they decided relativistic mass isn't real, so Richard Feynman.
He has, but not everybody.
Well, it's a controversy.
Yeah.
You've got people saying relativistic mass is real, and other people saying it's not.
It's just a definition of what the word mass means.
Yeah.
I think relativistic mass is real.
Yeah, that's right. But if you believe in relativistic mass, then there is problems, and he's going to give the problems here, I think.
I'll be gentle. If you've ever had a physics class, you've encountered a concept called momentum. Momentum has a meaning very similar to the colloquial meaning. Colloquially, once something has momentum, it's hard to stop. Well, in physics, we write momentum using this simple equation here. P stands for momentum, M stands for mass, and V stands for velocity. So you see, momentum can get big if mass is big or if velocity is big, or, I suppose, if both get big. Momentum is related to inertia. Something with a lot of momentum is hard to stop, but that could be a slow-moving but very massive train, or a very light but super fast bullet. That equation and those intuitions are pretty familiar. The problem arises when we start going at speeds that are very fast. At very high speeds, this equation no longer applies. The correct equation is this one here. We see that it looks like the normal momentum equation, but there is this added term, the gamma term. In fact, this equation with the gamma term is really the right momentum equation, and it works just fine even in day-to-day life. So I told you that the equation for momentum was P equals m times v, and also P equals gamma times m times v. How can they both be true? That's because at pretty low speeds, gamma has a numerical value of 1. Think about some really fast things. The fastest fastball ever thrown, gamma is about 1, or more specifically, this number here. How about a bullet from a sniper rifle? That's pretty fast, but gamma is still pretty close to 1. This time it's this number here. In fact, in order to make gamma to be 1% different from 1, which is to say 1.01, you need a velocity so fast that it can circle the Earth at the equator in a single second. So in any situation you've ever encountered, gamma is basically 1, and you can just drop it from the equation. But when you start going very fast, you can't do that anymore. At 10% the speed of light, gamma is 1.005. At 50% the speed of light, gamma is 1.155. And at 90% the speed of light, gamma is 2.294. When you get to 99% the speed of light, gamma is 7.089. And as you get even closer to the speed of light, gamma gets bigger and bigger. As you approach the speed of light, gamma becomes infinite. The equation here on the screen is how you calculate gamma. The symbol V is velocity and C is the speed of light. I just put it here if you want to play with the numbers yourself. If you don't care to do that, you don't need to worry about it, but I know some of my viewers really do love their equations. So let's get back to the idea that mass increases as you go faster and faster. How did that arise? Well, basically, it boils down to how we physicists introduced relativity to new students. Almost all people who are learning about relativity have taken an introductory physics class, and they're very familiar with the classical momentum equation. So what physicists did was to invent an idea that they called relativistic mass. Relativistic mass was just gamma times the actual mass. If you do that, you can then write the momentum equation as just momentum equals relativistic mass times velocity. That equation looks just like the introductory momentum equation. Taking this approach is helpful when you teach relativity. That way, you can focus your lesson not on new and unfamiliar equations, but rather on big ideas, especially the idea that momentum at high speeds acts differently than it does at low speeds. But this idea of relativistic mass comes at a price. The price is a misconception. For instance, people might take relativistic mass and Newton's equations for gravity and come up with some silly hodgepodge equations that don't accurately reflect what is going on. For instance, if a particle moving very, very close to the speed of light has a near infinite gamma, I've had people tell me that this means it has an infinite mass, and such a particle passing near the Earth will have an infinite force. This isn't true, but it confuses the heck out of some people.
So Lincoln is discarding what would be an easy connection between Newton and Einstein. So I think part of the problem is with relativistic mass, if you believe in that concept, then a spaceship, as it goes fast enough, should have a mass that might be the same as a black hole. So what happens then? Does it turn into a black hole? And Don Lincoln and others like him seem opposed to the idea that a spaceship might turn to a black hole that way. So
velocities are relative.
Sorry?
Velocities are relative.
Well, no,
There's no
if
absolute
you
velocity.
think relativistic mass is caused by velocity, then the mass could increase to being that of a black hole.
But I mean, if you sit in a spaceship, no one can universally agree that you're going at 0.9 the speed of light. You might be relative to the star that you're going past.
The person observing you, it's kind of like Star Trek.
Yeah.
You kind of like when you see Star Trek.
Yeah. So the question is, whose
Spaceship
spaceship would turn into the black hole, mine or the other person?
Yeah.
In special relativity as presented by Einstein in 1905, we are dealing with constant velocity motion between observers, and the problem becomes, for the observer of the object moving relative to him, does he think that the object's mass is increasing? And if it does increase, then relative to him, will the moving object then become a black hole if it goes fast enough? The interruption might have blurred at that point.
So what we're talking about is what's being taught to physics students about its relativity is wrong. What they're being taught is myth.
He says. I don't agree with that at all.
Well, that is the problem.
Yeah.
Well, in physics, when you teach physics, you talk about relativistic mass and rest mass.
Yeah.
And that's clear in the physics class.
Yeah.
So what you're saying is that relativistic mass is not rest mass, and in fact rest mass is the gravitational mass. So that's why
Well, I don't think they go into that properly when they talk.
I think they do.
When I taught, I don't think they went into it properly. Sort of like, I would think that you would, if relative to mass, then what confused me is, well, it should have a gravitational effect.
Well, the gravitational mass is the rest mass.
Well, when you've got rest mass, then there should be a gravitational effect.
There's no such thing as rest mass. All mass is due to dynamics.
Yeah.
No, that's not true.
It is. It's a Bavego.
Okay, so they start arguing among themselves, and some seem to believe in relativistic math and others don't, and they just don't seem to agree of some of the basic concepts in relativity as regard relativistic mass. Eventually they are told to stop so that I can carry on with the talk.
It is. It's a Bavego.
Well, if I'm stationary with respect to some, so so then what is the mass of an electron?
1.6.
Right, but why does it have non-zero mass? Well, I mean, what does
Because
that mean?
it's a Bavego.
I might be for general discussion.
So you're talking about it. All right.
So it's all dynamic in some
All right, well that's not a widely accepted.
Well, it then will alter. Because the same with where's the proton mass come from?
Let's put aside this for general discussion later.
It's controversy. It's controversy. You've got Don Lincoln.
Preach the controversy.
Don Lincoln versus the textbooks, and you've got other people like Don Lincoln. And I've seen other people like Don Lincoln saying their thing about there's no relativistic mass, and he seems to get the idea that, well, if you think relativistic mass has a gravitational effect, then you're getting things a bit wrong. So I found lots of myths in Einstein's relativity, and for instance, in 1905 he discards the ether, right? But then he starts talking of a stationary system, and that sounds very much like an ether frame. So he discarded an ether, but he's calling it by a different name. I've got another talk for that.
This is Ernst Mach, the Machian, the idea that gravitational mass is somehow in relation to the fixed stars.
Yeah, it would be connected to that. But
To talk about Mach's principle would also be another diversion. I didn't introduce anything about Mach, and I'm illustrating 3 problems in relativity which they can't stick to and want to throw up diversions.
You need to show the context. You can't just take that word out.
Yeah.
It may just mean stationary with respect to me.
Yeah.
So you need to show the context.
Yeah, well,
I think that if you show the context,
I got the maths. It's in my second talk. So from the maths, I'm saying it looks like he's using an ether frame, and that's in the next part of the talk. So my conclusion is many myths are taught to physics students about relativity. Einstein didn't clarify these things, and if someone else was co-author, then they're able to clarify these things better, because if it was joint effort, then you needed the other person to clarify things. When it gets to the issue of trying to fix these myths, of course, that raises a great deal of disagreement, the controversy, as we've got illustrated here. Some say relativist mass exists, some say it doesn't. So that's the finish of that talk. So my next talk is about the ethers. So I can go to that now, if you like. I've got 20 minutes, I think. So this is probably even worse. Slide.
Can I just say something, Roger?
Yeah.
Assumption that the second author would clarify things is not always true. Think of a supervisor and a PhD student who may have an idea but cannot overcome the authority. And I've seen that in work. One of the people I worked with years ago had a very fixed idea about a certain phenomenon. I can't give you the details because nobody could tell him he was wrong. Absolutely nobody. So if you wanted to publish your experiments, you had to go with his theory.
Yeah.
Okay?
Yeah.
So it's just if indeed Einstein's wife was an author, she might have been in the situation that she couldn't quite convince him or get him to check.
I think with the wife there is also the issue.
It's a speculation.
With the wife issue, there was some sort of deal between Einstein and his wife over money. So she wasn't allowed to talk if she wanted the money. So that was one way of silencing her.
He also struggled with a lot of the mathematics of differential tensor calculus. So Emmy Never was a German mathematician who did a lot of that work, or helped him with a lot of that work.
Yeah.
He was also under-recognised.
Yeah, there was all that, and his wife was also doing maths with him. So this might be more controversial. So. When Einstein wrote his paper 1905, special relativity, what he omits to mention lots of things, is there's a particle theory of light according to Newton, and you've got a wave theory of light by Huygens and others. So he's not making it clear what is he going by. Is he going by, how did that happen? So he's not making it clear which one he's going by. So when he starts talking about a rod with endpoints A and B, he's talking about light leaving from A and going to endpoint B. And the rod is moving with speed v in the same direction as the light is moving with the speed c. But he's not saying, is he considering that as a wave of light or as a particle of light? And depending on how you treat the light, you get different maths. So what you got is light leaving from endpoint A, and the initial position of A is, I'm calling endpoint A, subscript O, and initial position B is position B, subscript O. So what happens is this rod moves to this new position. So light leaves here, and when it gets to here, this endpoint has moved to the new position. And something similar occurs on the return journey. So light is going back from B to A. Is it? Oh, I've got my ear. So I'll show you. So light leaves B when it's at position B1, and A is now at position A1, but that sort of moves as well. That moves again. So when light gets to A, it's at position A subscript 2. And Einstein's not gone into detail in his paper about this. This is all missed out. So,
I mean, in the paper he describes it by analogy to sitting in a train, and
dealing with the trains was not something in Einstein's 1905 paper. It was something Einstein talked about later. It was something I was not talking about. And
throwing a ball or something. So I mean,
he gives you the maths, and he doesn't say. It doesn't say what he's using.
I mean, so the Huygens theory, the wavefront propagation, would give you the same travel time as imagining a ray bouncing off a particular point in the mirror. So I think he can omit that discussion for the treatment, but maybe it's interesting.
Well, he doesn't give it.
Yeah.
So in the Newtonian calculation, it's two different calculations. You've got for a light particle, it's this. This is what you get if you're treating it as a light particle. You end up with that. But and for the return journey, you've got that. You end up with that. So you end up with the equation for the rod as being that. And that's from treating light as a particle. So next we need to do the Newtonian calculation for when it's a light wave. And that means you've got an ether frame. Light, it has as a wave you would think would have a medium, and you would then think you would have an ether frame. And the Mixel-Morley experiment was trying to measure light speed relative to the ether frame, and was treating light as a wave as per Huygens theory. So instead of a particle, you've got a wave. So you need an ether frame, and we could denote that as position A subscript O. So light moves, you're treating that as the ether frame position A subscript O, and light's going from there to position B1. And so the mass you get is that. And for the return journey, you get this. So contrasting the two calculations, rod length without an ether frame is that, and rod length with an ether is that, and Einstein uses that equation. He's using the equation of light being a wave.
So the difference in what you get comes down to whether you take, whether you change the frames on the process of taking the difference of the velocities or the sum of the velocities.
Yeah. You would have to say whether you've got an ether frame for the calculation. So Einstein gives that, and rearrange you get that, which is the one with the ether frame. So Einstein's maths, based on that, seems to be based on Huygens theory and not on the light as a particle theory. So it's an ether theory. So Einstein does a calculation to get rod length based on using ether. He seems to say there's no ether, but he uses ether anyway in his maths. Now there's two ways to look at that. Einstein is mistaken when he says no ether, and really his theory is an ether theory. Or Einstein's bad at maths, and really he had no ether, as he seems to claim, then his maths needs amending. So you've got a problem there. What are you going to do with this problem? Is he got an ether theory or not? And should have mentioned that Lorentz has an ether theory. Lorentz theory is an ether theory. So Einstein seems to be doing the same as Lorentz by using an ether theory, and then using the relativistic factor on top of that.
I mean, the maths comes down to the Lorentz transformations. There's a kind of ether, but what people were considering at the time as an ether would be something that the planets, for instance, move through. So it's fixed. So the experiments were would the light ray be retarded in one direction and accelerated because of its motion relative to
What I was talking about in the math presented was light moving relative to a rod. If dealing with Earth moving, then we'll be dealing with similar type of maths, and I don't know if the interruption managed to blur that issue.
There is the null interval in Minkowski space is what everyone agrees on. The amount.
Minkowski serves as another diversion. I did not mention Minkowski. I was dealing with relativity as presented by Einstein in 1905 and querying how he connected to earlier work of Lorentz. Minkowski with space-time came after 1905. So once again they are not wanting to stick to what I was dealing with.
The time between the separation between two events, the bit when it's emitted, the event where it's reflected, and the event where it's received again, how they add quadratically the difference between the space and the time, everyone agrees on that. That's not quite the same as an ether frame that people were imagining when they were thinking it's like a sea that you're moving relative to.
Yeah.
So
because it's all like when you go with Lorentz, the Michelson-Morley experiment, looking at that, and it's all like you're having problems with the ether frame. So he was adding the relativistic factors to kind of try to compensate for that. And then they're saying, oh, Einstein's got a different theory, you don't need an ether. But when you look through the math, he seems to be doing on this little bit the same as Lorentz. He's using an ether theory and then trying to cover it up by using relativistic factors. So is Einstein's theory really the same as Lorentz's theory about the ether?
And the standard answer is that the ether is the causal structure of space-time, but that's not something that you can just think of in terms of
that's all later stuff that's come up further on. It's all like you had Lorentz's theory before Einstein's theory, and Lorentz had his ether frame theory. Lorentz ether was his version of ether, and when you look at Einstein, you seem to have this myth, where he's using the Lorentz ether as well.
I think I'd argue that this
is
a conceptual difficulty or a pedagogical, didactic problem, but it's not a mathematical problem. The maths
you've got maths and you're using words. And so you're saying, well, this maths, you've got no ether. But when you look at it in the historical context, you're still using Lorentz ether by the looks of it.
Where it becomes important again is things like redshift, because
redshift would be another diversion. I had not mentioned redshift, and the 3 examples I gave there was already too many problems without going on to a diversion about redshift. Once again, they're not wanting to stick to what was presented.
There are people that argue that rather than presupposing a fixed speed of light and then driving an expansion of the space, you could not have that presupposition.
It's the words you're using to talk about the math, it's all been messed up. And I've pointed out the 3 cases now. The first one, it's a myth about what they tell you about Lorentz transformations reducing to Galilean transformations, and there's a controversy, thinking relativistic mass is a myth, and then there's this problem I'm pointing out in the ether. It's sort of like Einstein's relativity has not been properly clarified, and what's being taught to physics students is just all being messed up. So that's the end. Okay.
Do we have any questions from the Zoom? Or comments from the Zoom audience?
I think Mike was waiting.
Any questions from Zoom?
I think so.
There might not be able to hear you. I think you might need to talk into the microphone. Please.
Mike, have you got a question from Zoom?
No question.
Hey.
Okay. Anybody got a question from Zoom? Sorry, do I need to talk into the microphone? That's up there.
No questions, but we can hear you fine. Thank you.
Okay.
Okay. No questions from Zoom? Okay, any more from the audience?
So, about the first part, I guess the way I would look at this is not to say that what physics students are being taught is wrong, but it's not being phrased very precisely.
You're saying not phrased properly, that would be moving the goalpost as far as I'm concerned. I have presented what the textbooks say about Lorentz transformations. To say that the textbooks are not phrasing things properly, then that would mean a revision to the textbooks. In other words, move the goalposts.
You can make the phrasing more precise in the following way. Suppose you have a physical system with a characteristic velocity and a characteristic length scale. So in physical problems, when you deal with physical situations, you have a characteristic length scale. Like if you're dealing with problems involving the solar system, you have a length scale. Problems involving daily life, you have a certain length scale.
Yeah.
So suppose you have a physical problem involving a characteristic velocity and a characteristic length scale. Now, you can, if you take that situation and you assume the speed of light gets larger and larger, compared to the geometric mean of the length scale and the time, then the equations will approach, Einstein's equations will approach Newton's equations.
Yeah.
And what I think they're trying to express in, when they say this in physics, is that this is why we believe relativity is true, but we still use Newton equations in daily life, because the length scales that we're dealing with are sufficiently small.
Yeah, but
so they're just omitting that.
Well, when it gets to the correspondence principle, they haven't got it.
So you're making you're trying to make, they're not making a philosophical claim, they're making a practical claim.
Well, it's still got to be a definition claim, isn't it?
It's not a definition.
There's a subtle thing that's not examined, and that's exactly this length scale in X. So when there was this discussion, but that's why they said that we can not think about the change in X, we can just think about the T prime tending towards T in the limit of...
well, they're assuming that we're dealing with, I mean, you're always dealing with a certain length scale.
Yeah, but perhaps for relativistic events, for example, events in our atmosphere when charged particles are coming in close to the speed of light, it might be what you said. This might be some relation between the Planck scale and
bringing in the issue of Planck scale would just be another diversion. I did not mention it. There was no reason to mention it in the context of what was being dealt with.
No, don't go down to the Planck. I'm saying that if you're dealing with things on the level of solar system, right, then that's less than 10 to the 20th meters, right?
Yeah.
So if you consider events less than 10 that have length scales less than 10 to the 20th meters, and you take lower velocities and assume that C gets larger and larger, then those equations will reduce to Newton's equation.
But already with the perihelion of Mercury, we have enough of a deviation from that, because that's
well, that's general relativity, not special.
Oh yeah, that's true. Yeah, that's true.
No, it's wrong there as well. When you go to general relativity and talking about the Newtonian, I'll go on to that, but it's sort of like when I'm reading Kip Thorne, he's pointing out that Newtonian tidal theory is the same as general relativity, just in a different language. When you're talking about Newtonian gravity theory, you're only having half of the deflection of the light. But when you take into account tidal force, then you get the full effect.
Then you get the spaghettification.
So you get the full. So Newtonian tidal gravity theory is the same as Einstein's relativity, but that's not what they teach again. They don't teach you that. They teach the wrong thing again. So what they're doing is they're just teaching myths.
It's always an approximation.
Well, they're telling you things that are wrong.
See, they're not they're not making a philosophical claim.
Well, they're not telling.
Practical claim.
They're not telling you that they're making an approximation. So they're not telling.
Physics is always
They're
making
telling you.
approximations.
They're telling you the first myth I tell you, and they're telling you Lorentz transformation is reduced to Galilean transformation, and they don't tell you, oh, that's an approximation. They don't tell you that, and so that you can get away with the delusion that they are.
If you precisely define the mathematical limits involved, then Lorentz equations.
Well, they're not teaching it precisely to students.
You're always teaching approximations.
Yeah.
But
they're not making.
I mean,
they're not making that clear to students, in my view.
In physics 1,
yeah,
you don't tell people Newton is wrong.
Well, he's not wrong.
These are the.
Well, I disagree with that. I think Newton is right, and it's just these other people on relativity. They've misunderstood. They've misunderstood Einstein, and then they're saying that Newton's wrong, but he's not.
But they
so
don't
it's all myth. It's all myth.
They don't say that those equations are only approximate. The F equals
exactly.
equation is only approximate.
Can I? There may be a question on Zoom here. Is there a question on Zoom? So who said? Albrecht, you've got a question? Have you got a question? This comment.
Which has to do with the test of ether or not, and that is the point of Einstein's famous first paper of 1905, where he has discussed about the constancy of the speed of light. And I think there is a very funny statement of him, if you follow his calculations in this paper, and we know that that is about the speed of light for a moving system. We know that we need to measure, for measuring the speed of light, we need two clocks on both sides of the measuring system, which have to be synchronized, of course. And Einstein has in this paper given a rule, a prescription how to synchronize clocks. And Einstein has said one should use to synchronize clocks light signal with the assumption that speed of light is constant in any frame. And if you allow synchronized clocks in this way, the result of the measurement will always be a constant speed of light, because what Einstein has done there is circular reasoning. And he makes a precondition, uses it to synchronize clocks, and as a result, the measurements with these clocks will reproduce the assumption, and that is that the speed of light is constant in any circular system. And I would recommend anyone who is interested in this point to look into his paper. It's very, I think, surprising and a bit shocking that Einstein has here made such a logical, what would be psycho. It's not really logical.
This question about clocks and light speed constancy. Well, my talk was about three problems in relativity: the Lorentz transformations, relativistic mass, and then the ether. I was not dealing with that issue of clocks and light speed constancy. I point out that my talk is not about that, but there are still problems with that issue. It's like he didn't pay any attention to what I was talking about with the three issues and wanted to talk about something else instead. All of the believers in Einstein's relativity seem to use that tactic. They did not stick to what was being pointed out to them in the talk and instead wanted to bring in other issues. Conclusion: it is one of the tactics that Einstein relativity believers use. Whenever possible, throw up a diversion.
You're saying it's tautology?
It's tautology.
It's tautology.
Yes, tautology, I think is the right word.
A choice of what to loosen. You could, instead of loosening, he starts with what we consider a rigid measuring rod, and he doesn't loosen the time, so the measuring rod's rigidity has to be loosened. It has to have contraction or expansion, relative contraction, expansion.
Well, a lot of detail he's not going into in this paper. So I gave a paper referenced by Rolf, who's talking about myths and relativity. The other myth he was going into is about the speed of light, and what is meant by the speed of light has undergone numerous changes anyway. So if you're bringing up that issue of the speed of light, then that's that's changed as well.
If one is bringing it up, I'm not bringing it up.
So, no, sorry, he is bringing up that. So it's another issue of more myths that is.
Okay, I think we should close this discussion now, because we need to come to the last speaker and we need to make some rearrangements for this.
Arguing with them continued after that talk and will be the subject of part 2. With believers in Einstein's relativity, they get very upset if their beliefs are challenged. They're not really open to the possibility that what they believe is wrong, hence their tactics of throwing up diversions. I think the problem they face is, if a few basic things about relativity they believe are wrong, then it throws under doubt numerous additional things they believe as being wrong as well. Anyway, I will continue in part 2.
Nicola wants to use... Thank you. Thank you very much, Roger, for that interesting presentation. Now, Nicola wants to use flip charts, so we're going to have to point that way so people in Zoom can see us. So we're going to have to turn our chairs round to look in that direction. So, where do you want to put your flip chart? How far away can it be?